Polynomials lesson number 2. Here we're doing factoring of polynomials. Well, before we can start factoring the more difficult ones, we have to review some factoring here. So let's quickly look at, I'll even put one on that they don't have. Let's start with x squared minus 4x minus 21. Start there. Remind you of your sum product factoring. Sum equals, product equals, factors equals. So your SPF. Sum is your middle term. What two numbers will add up to give us the negative 4? Your product is the first term multiplied by the last term. So in this case, your product is going to be 1 from the beginning, from the first term, times the negative 21, so negative 21. What two numbers will multiply together to give me negative 21, and then we'll add together to give me negative 4? So when we look at this one, we know that because the sum's negative and the product's negative, we need a negative and a positive, and the larger one is going to be the negative. So negative 7 and a positive 3. So we have x minus 7 and x plus 3. Let's now go through where the leading coefficient is not 1. So in this case, we've got sum product factor. We first of all look, is there any GCF that you can pull out? No, there's not. So your first step of factoring, GCF, there's none here. So we're going to pull out sum of, again, the middle term. So 7. And a product, again, of the first times the last. So 6 multiplied by negative 3, which is negative 18. So if we look at the factors in this one, we've got what two numbers are going to multiply together to give us negative 18, add together to give us 7, and we need two negatives, a negative and a positive, because it's negative, and the bigger one has to be positive. So we've got 9 and 2, negative. At this point, we've got a couple options on which method of factoring you use. I'll show decomposition, and then I will show the shortcut method as well. So the first one is decompose that middle term. So we've got 6x squared. Decompose that middle term into the two components that we just wrote right here. And I like to put the negative 1 first. Less mistakes get made. And then minus 2x plus 9x minus 3. Then we're going to group the first two, group the second two, and pull out any GCFs that we have. So between 6x squared and negative 2x, I can pull out a 2x. Leaves me with 3x minus 1. And pulling out of the next part, we've got plus from the 9x and the 3, I'm going to pull out a 3 plus 3. Leaves me with 3x minus 1. Those two parts in the brackets better be the same. They're common. I'm going to pull that, factor that out in front as a GCF. Leaves me with 2x plus 3. There's your decomposition method. Second method that you could use also goes from, you still got to do that sum product factoring. Got to start there. The second method that you can use is a shortcut method. X plus 9 and x minus 2. Doesn't matter which order you write them in. Write them in one order, write them in the other order. But with this one, I took that 6 and multiplied it to the negative 3 to get the negative 18. So because I took that 6 and multiplied it by the negative 3, I'm going to have to compensate back here with my answer and divide both components by the 6. Take that down to lowest terms. So 9 over 6, divide them each by 3, we get plus 3 over 2. And the 2 and the 6, I get x minus 1/3. When you still have a fraction after this step, we're going to just bring the fraction part up in front. So we've got 2x plus 3 and 3x minus 1, which, as you can see here, gives me exact same answer that I had with the other method. So whichever one of those methods works for you, great, go ahead and use them. Looking at the next one. Again, the first thing that you got to do is pull out any GCFs. I do have a GCF here. I could pull out an x out of all of them. So going to be 2x squared minus 3x minus 14. And then now we're going to use our sum of -3, our product of 2 times -14, so -28. And we need two numbers that are going to multiply together to give me -28, add together to give me -3. So we've got -7 and 4. I'll use the shortcut method in this one. So we've got x minus 7, x plus 4. X. But because I multiplied the 2 to the -14, I'm going to have to divide both of those by that 2. Take it down to lowest terms. That one's already in lowest terms, so 2x minus 7. And this one can go down, x plus 2, factored. The next one, when we've got two terms only, some product factoring, yeah, it will work. We can use decomposition, but it's a lot easier to use it as a difference of squares. Whenever you factor difference of squares, you're always going to get into conjugate binomials. So, really what this is saying is 49 is a perfect square, x squared is a perfect square. That's like saying 7x squared minus 36 squared is 6, y squared squared. Because we had y to the 4th. A conjugate is the square root of the first, which is 7x, and the square root of the second, which is 6y squared. Putting that down twice, and then putting the opposite signs in between. So 1 plus 1 minus. There's a set of conjugate pairs, and that is now factored. So using the information from lesson 1.1, we now want to divide to see if this is a factor. We'll know it's a factor because it will have a remainder of 0. So if it's a factor, it will have a remainder of 0. Let's start with that first. I'm going to use synthetic division. It's just a lot faster use. So 3, -2, -1. Box that in. And remember, we are not using -1. We're using the additive inverse of a +1. Bring down the 3. 1 times 3 gives me 3. Add 1. 1 times 1 gives me 1. Add 0. The last number is our remainder. We were looking for a remainder of 0. I've got a remainder of 0, so yes, the first one is a factor. Let's check out the second one. 3, -8, -1, -2. Box that baby in. And now I'm using, instead of the x minus 3, I'm using a +3. Opposite sign, additive inverse. Drop down the 3. 3 times 3 is 9. Add 1. 3 times 1, 3. Add 2. 3 times 2 is 6. Add 4. That is not 0. Therefore, no, the second one is not a factor. Third one. 2, -1, negative 17, negative 11, 6. And because we've got x plus 2, I'm going to use the additive inverse, negative 2. Drop down the 2. Multiply, negative 4. Add, negative 5. Multiply, 10. Add, negative 7. Multiply, positive 14. Add, gives me negative 3. Multiply, gives me 6. And then, just a minute, that should have been a positive 3, there we go. Negative 6, there we are, and 0. So yes, this is, x plus 2 is a factor of that big polynomial. But we've got another way that we can do this. How can we do it without having to go through the whole process of dividing? Well, in walks our function notation. In function notation, we're saying things like f at 2. What is the value of the function at the point of an x of 2? The same thing's going to happen here. In the first question, I'm going to see what happens when I take this value of 1 and plug it back into the original polynomial. Let's see what happens here. So, p of 1 equals, so we started with 3 times 1 squared minus 2 times 1 minus 1. Gives me 3 minus 2 minus 1. 3 minus 2 minus 1 gives me 0. Ooh, interesting. I get the value of 0, which happened to be the remainder when I did that. Huh. Coincidence? I think not. Let's check out the second one and see if that's going to hold true. This time I'm going to do p at 3. So what's the value of the polynomial at 3? Plug in your 3 anywhere you see an x. So 3, oh, there's an x, so 3 cubed minus 8, there's an x, 3 squared minus 3 minus 2. 3 to the 3, that's 27. 3 times 27 minus 8 times 9 minus 3 minus 2. So then 3 times 27, that is 81. Minus 8 times 9, 72. Minus 3 minus 2. 81 minus 72 minus 3 minus 2. So we've got 9 minus 3 is 6 minus 2, that is 4. Oh, look at that. Cool stuff. Same is going to hold true if you use the third one. You can try that yourself to prove it to you. This next part in your book there goes through and explains what I just said. And that is, when a polynomial is divided by x minus a, the remainder is related to the polynomial and the constant term of the divisor. So in this case, when we do our whole division of this one, we got a remainder of 47. The same thing will happen if we take our divisor and we take our polynomial and we evaluate at x equals 2. This is the same value we use for synthetic. It's the additive inverse of x minus 2. So we're going to use x equals positive 2. And then we just evaluate it through, just like I showed you. And you'll always come up with the remainder each and every time. This, right, what we've just described is known as the remainder theorem. So, going to our bit.ly link, and you're going to sign in with your Google account that I gave you. We're going to bit.ly / today's is P, capital P, J, 8, Z, B, X. That's a Z, not a 2. Go there, answer this question up for yourself. So the remainder theorem states when a polynomial is divided by a binomial, the remainder is P at A. Notice carefully here, X minus A, I'm using the additive inverse of A. So again, showing what's happening here. If we take our division statement, which you learned in 1.1, plug in an A for the X, and let's start working it through. So that means we're going to plug in for the X, the A, so we've got A minus A times the Q of A. A minus A is always going to be 0, every time. 0 times whatever the quotient is always going to be 0, leaving you just with the remainder. So that's the algebra behind the scenes. All right, let's try this one out. Determine the remainder when that is divided by X minus 3. Synthetic or function notation. We're going to use remainder theorem because that's what we just learned. So let's try that one out. So we've got P at, and because it's negative 3, we're using a positive 3. P at 3 gives us 2 times 3 to the 4 minus 5 times 3 cubed minus 5 times 3 squared plus 5 times 3 plus 3. That gives us 3 to the 4th, that is 81. Because 3 squared is 9, squared again is 81. So 2 times 81 minus 5 times 27 minus 5 times 9 plus 15 plus 3. And if we punch that into your calculator, you could have done it right from the beginning. You would have gotten 0. So the remainder is 0, meaning, again, that X minus 3 is a factor of that original polynomial. All right, let's try X plus 2. Same process. We're using P at negative 2. Gives you 2 times negative 2 to the 4th minus 5 times negative 2 cubed minus 5 times negative 2 squared and plus 5 times negative 2 and plus a 3 on the end there. All right, let's do this one up. Negative 2 to the 4th, that is the same as 2 to the 4th because it's going to be a positive 16 minus 5 times negative 2 cubed, that's going to give us negative 8 minus 5 times 4 minus 10 plus 3. Again, punching that into your calculator, working it through, or doing it right from the beginning. You're going to get a remainder of 45. Doing your thinking further question there, does a polynomial have to be written in descending order in order to use the remainder theorem? Come up with a yes or no there. Okay, so in that first example I just did, the remainder was 0. This is a special case of the remainder theorem because we said it's a factor. So they're going to give it a new name. Factor theorem. So if you get 0 as a remainder, it is now called factor theorem because it was a factor. All right, second question for you. Again, still at that bit.ly link. For the polynomial p at x, if p at 5 equals 0, what is the related binomial factor? So if this holds true, then which one of those was the factor that we actually divided by? Answer that now. Let's look at your example number 2 now. Which binomials are factors of that original? Well, you got your two options. You could use synthetic division. You could use the factors theorem. Whichever one works for you will work here. I'm going to show you factors theorem because that's what we're looking at right now. But realize that synthetic division would work as well. Your whole thing is, if it is a factor, remainder has to equal 0 in order to be a factor. So let's try out that first one. We're doing p at, and because it's x plus 1, we're going to use the additive inverse, negative 1. Gives us negative 1 cubed minus 6 times negative 1 squared plus 5 times negative 1 plus 12. Hammering that through. Yeah, that's a 0. Boom. First one's good to go. Let's check out that second one. We're doing p at positive 4 now. So that gives us 4. Oops, I'm not doing it in the right order. I'm doing c, but that's okay. 4 cubed minus 6 times 4 squared plus 5 times 4 plus 12. Hammering that through your calculator. I know your best friend is a calculator. There you go. You got 0 as well. So yeah, c is also a factor. Let's try out that third one. And just as an aside, just thinking, how many factors should there be or could there be of this original? Huh, really good question. If it's x cubed, that probably means that we had x plus or minus something. So we'll say x minus a times x minus b times x minus c. And those could be plus or minuses, doesn't matter. The only way that we're going to get an x cubed is if we are multiplying 3 x's together. So there's probably 3 factors. Let's check out b for ourselves now. P at positive 3, oof, that was a close one, gives us 3 cubed minus 6 times 3 squared plus 5 times 3, ooh, that looks like garbage, plus 12. All right, shoot it in your calculator, and that gives us, ooh, look at that, 0. Yeah. Oh, I just found 3 factors. Can D be a factor? No. We just found 3 factors. There's no way we can have a 4th factor if we have x cubed. It's not going to happen. Let's just prove it to ourselves. Let's do p at negative 4 gives us negative 4 cubed minus 6 times negative 4 squared plus 5 times negative 4 plus the 12, and the calculator says negative 168. That is most definitely not 0, and that is not a factor. Okay, bring that together. From that original polynomial, if we talk about this one, this is the one from your notes, not just the one we just did, but the example 2 in your notes. It also had 3 factors. But if we factored out that polynomial, and if you look at the example, you got these 3 factors. If we reverse the process, if we expand those 3 by multiplying them together here, we will get back to the original polynomial. Look carefully at this. This is where the key is here now. That 10. The way that we get that 10 is that we multiplied, when we expand this, we're actually multiplying the negative 1 times the negative 2, and then that number gets multiplied by the 5. So that's what it's saying here. The 1, the 2, and the 5, if we multiply those together, we'll get 10. Positive or negative, that's not a big deal right now, but just realize that those numbers, 1, 2, and 5, will multiply to the 10. Ooh, this is going to be good information. This is going to help us out here. So if a binomial is a factor of a polynomial, then A is a factor of the constant term, meaning that the 1, the 2, and the 5 are all factors of 10. They have to be. We're going to use that to our advantage now. And now, for your viewing pleasure, because I know everybody has been waiting, hey, when is that lady going to talk and explain something? Here we go. Let's listen to her.
Factor fully 2x cubed minus 9x squared plus 7x plus 6.
And this is coming out of your example number 3, the one that they do for you.
Okay, so I'll let p at x equal 2x cubed minus 9x squared plus 7x plus 6. I know that if I can find an integer, a, so that p at a equals 0, then x minus a is a factor of p at x. I also know that if x minus a is a factor of p at x, then a is a factor of the constant term in p at x. Since the constant term is 6, I'll list the factors of 6. 1, negative 1, 2, negative 2, 3, negative 3, 6, and negative 6. I'll start by evaluating the polynomial for x equals 1. 1 cubed is 1. 1 squared is 1. So, that's 2 minus 9 plus 7 plus 6, which is 6. Since p at 1 does not equal 0, x minus 1 is not a factor of p at x. Now I'll try x equals negative 1. Negative 1 cubed is negative 1. Negative 1 squared is 1. So that's negative 2 minus 9 minus 7 plus 6, which is negative 12. Since p at negative 1 does not equal 0, x plus 1 is not a factor of p at x. Now I'll try x equals 2. 2 cubed is 8. 2 squared is 4. So that's 16 minus 36 plus 14 plus 6, which is 0. Since p at 2 equals 0, x minus 2 is a factor of p at x. Now that I know one factor, I can divide to find another. I'll use synthetic division. I'm dividing by x minus 2, so I write 2 on the left. I write the coefficients of p at x on the right. 2, negative 9, 7, and 6. I'll bring down the 2 and multiply it by 2 to get 4. Negative 9 plus 4 is negative 5. Negative 5 times 2 is negative 10. 7 plus negative 10 is negative 3. Negative 3 times 2 is negative 6. 6 plus negative 6 is 0. The original polynomial has degree 3, so the quotient will be a polynomial of degree 2. So, the division statement will look like this. 2x cubed minus 9x squared plus 7x plus 6 equals x minus 2 times bx squared plus cx plus d. b is 2, c is negative 5, d is negative 3. So, 2x cubed minus 9x squared plus 7x plus 6 equals x minus 2 times 2x squared minus 5x minus 3. I'm supposed to factor fully, so I still have to try to factor 2x squared minus 5x minus 3. I need to combine the factors of 2x squared with each pair of factors of negative 3 until I find a sum of negative 5x. The factors of 2x squared are 2x and x. The factors of negative 3 are 1 and negative 3, and negative 1 and 3. We'll try using 1 and negative 3. 2x times negative 3 is negative 6x. X times 1 is x. Negative 6x plus x is negative 5x. That's the sum I'm looking for. So, the factors of 2x squared minus 5x minus 3 are 2x plus 1 and x minus 3. So, 2x cubed minus 9x squared plus 7x plus 6 equals x minus 2 times 2x plus 1 times x minus 3.
Riveting. Nice. Nice. What she used there was factoring by inspection. I didn't show you that method. She showed you it there. Use it if you'd like, or the other two methods will work just fine for you. Let's try one out for ourselves. And again, just like always, try to get ahead. Try to do it yourself. Check in with the answer. Here we go. Let's factor this one fully. So we know that when this is factored, the factors are going to be factors of 2. So we're going to call these, I like to call them potential zeros. For our potential zeros, it's going to be any plus or minus, any positive or negative of the factors of that 2. The factors of 2 are 1 and 2. So the only potential zeros that we could have are positive 1, negative 1, positive 2, negative 2. Start looking through and saying, okay, well, which one would work? The ones are the easiest to start with. So try it. You only need to find one. So I'm going to use, hey, let's try x equals 1. So let's do p at 1. 3 times 1 cubed minus 4 times 1 squared minus 5 times 1 plus 2. Punch that in and through. We know this is not going to equal negative, or not equal 0. So it's, you don't even need to get to numbers. As soon as you realize it's not going to be 0, no. So then let's try p at negative 1. So then 3 times negative 1 cubed minus 4 times negative 1 squared minus 5 times negative 1 plus 2. Punching those through, yeah, we do get 0. So that means, this is the key here, if p at negative 1 worked, that means x plus 1 is a factor. The factor is x plus 1. Now we're going to use our synthetic division. Whatever number you use that worked there is the number you're using in synthetic. So 3, negative 4, negative 5, 2. Drop it down, 3. Multiply negative 3. Add negative 7. Multiply 7. Add is 2. Multiply negative 2. Add 0. If you do not get 0, you did something wrong. Start again. You have to get a remainder of 0 for it to be a factor. This is now saying that x plus 1 multiplied by 3x squared minus 7x plus 2. That equals the original polynomial if we multiply those together. But I'm not fully factored. I need to factor this part. You got options. You can factor that quadratic like you've always learned how to factor. But you know what? I'm going to show you something different. I could use some product factoring like I showed at the beginning. If you're comfortable with it, go ahead. I'm going to do this. I know that my factors still have to be a factor of this last one, which is still plus and minus 1, plus and minus 2. already I know that a p at 1 did not work, and I used p at -1 and it worked. So I could try to find another one. This is sometimes a little bit tricky. So this could be tricky sometimes if your factors are not of a binomial form, x plus or minus something. If it's like 2x plus or 3x plus, this next part is not going to work. So it will work sometimes, sometimes not. So factoring it like quadratic, that will always work though. So we're going to look and see if we can find another one that will work. Let's go through, and I'm going to try p at 2, and when you punch that into 3 times 2 squared minus 7 times 2 plus 2, yeah, that equals 0, so I put the 2 into this polynomial. And I'm just going to continue with synthetic division, right off of the last one I just used. This time I'm going to use the 2. Drop down the 3, that gives me the 6. 2 times 6, that gives me 12, and add, that gives me 5. Let's start that again. What kind of stupid thing is that there? How did I bring down a 6? Let's bring down the actual real number is a 3. 3 times 2. Now that is a 6. There we go. That's where I got the 6 from. And add those up. That gives me -1. This is looking better. 3 times 2, that gives me -2. That's 0. I better get a 0 or else I know I did something wrong, and that's how I knew I messed that baby up. This now tells us, from the first one, we had x plus 1 as a factor. From the second one gives us an x minus 2 as the factor. And the third one is now saying 3x minus 1 as the third factor, right from here. So those three factors work together. This means that the original polynomial, 3x cubed minus 4x squared minus 5x plus 2, is going to be equal to the three factors that we just came up with in factored form. X plus 1, x minus 2, 3x minus 1. Whoa, yeah! You just factored a cubic polynomial for your first time. Go through, answer your think further, and your to discuss the ideas. We will discuss those in class first thing.